Alright, welcome back everyone to yet another AMC problem solving strategy video. My name is Sol, and today you might notice that we don't have a problem on the board. And that's just because, well, I'm going to be talking about more so some theorems that are necessary to be able to solve some problems, and then next video we'll probably go over a problem from the AMC that will incorporate all of these theorems that I'm about to tell you about. So I decided to make a video on number theory, mainly just because, well, it's never emphasized in a standard high school curriculum. I mean, there's a lot of emphasis on geometry and algebra, especially algebra, and like a touch of combinatorics if you take AP statistics, but that's about it, and like, that's it. We never actually touch number theory. And so I thought, well, I mean, over this past summer, I've attended some number theory camps, so maybe I'll just share some of my knowledge so that you guys can actually formulate formal solutions for these number theory problems instead of just guessing your way through them, like I did on my number theory problems when the past few years that I've computed. So yeah, let's jump right into it. Alright, so the first theorem we're going to be talking about is the Chinese remainder theorem. Now, if you guys have been solving contest problems for a while, you guys might have seen this theorem being mentioned in, say, the solution to a number theory problem without actually knowing what it states. And I want you guys to keep this in mind. The Chinese remainder theorem is not necessarily a formula you can apply to a number theory problem, but it's more so a concept that you can use to your advantage to solve number theory problems. So what it says is that if I have some positive integer, n, so n is an element of the positive integers, and I have this system of congruences such that n is congruent to x sub 1 mod m sub 1, n is congruent to x sub 2 mod m sub 2, and so on and so forth, up until x sub a mod m sub a, then there is some unique solution of n can be written as mod, there is some unique b that n is congruent to mod m sub 1 times m sub 2 all the way up until m sub a. That's not formal notation, you should probably use dots. So anyway, yeah, just as a recap of this statement, if I have a system of congruences such that the moduli are all relatively prime to each other, then there is a unique solution for n mod the product of all of those moduli. Okay, how is this helpful, right? Where are we supposed to use this? Well, certainly, maybe not on the AMC, but say on like Mao State or Mao Nationals, you've gotten a question like this, like this, and you're not quite sure how to approach it because, well, I mean, certainly my first approach would have been to try to find a pattern. So maybe like, oh, well, 7, let's go through the powers of 7 mod 100. So we have 7 first, and then we have 49. 49 times 7 is 343, so that mod 100 is 43. And then we just kind of have this go on forever and ever. Well, what I would not have realized was that the cycle is actually quite long, but instead of trying to attack this problem in sort of a naive way like this, we can actually approach it using the Chinese remainder theorem. So basically, this 7 to the 29 mod 100 can be likened to this statement right here, where 7 to the 29 is kind of our n, and we are trying to find b, and we can treat 100 as a product of relatively prime moduli. And in this case, well, since we want to factor 100 into relatively prime numbers, I think it'd be smart to use 2 squared and 5 squared. Right? We're not going to use 10 and 10 because those aren't relatively prime to each other, or 2 and 50. We have to use 4 and 25. So we can write 7 to the 29 mod 4 and 7 to the 29 mod 25, And look, these are basically these statements that we have over here, right? We have a system of congruences, and we can much more easily solve these than straight up mod 100. And then we can combine those into mod 4 times 25, or again, mod 100, to get our unique solution. So yeah, that's about it. Let's move on to the next theorem. Alright, so the next theorem we're going to talk about is Fermat's little theorem. And basically what Fermat's little theorem states is that if we have two positive integers, a and p, so two positive integers, a and p, such that the greatest common divisor of a and p is 1, meaning they're relatively prime, and p is prime, then we have that a to the p minus 1 mod, or a to the p minus 1 is congruent to 1 mod p. Okay, so this theorem, it's very elegant, right? It's an actual statement. It's a kind of an equation, right, that we're all used to. But if you think about it, I mean, what exactly are the uses, right? Rarely do we ever take a number mod a prime number in contest problems. I mean, maybe if you think about it, when we were talking about Chinese remainder theorem, we talked about splitting a number like 100 into 2 squared and 5 squared, but 2 squared is not prime and neither is 5 squared, so how is this supposed to be useful outside of just prime numbers? I mean, sure, you can solve, you can kind of simplify things like, we'll pick on 7 again. You can kind of simplify things like 7 to the 13th mod 13. I mean, you know that this is going to be, well, 7, because 7 to the 12th we know is congruent to 1, meaning if we just multiply on another 7, it's just going to be 7 mod 13. So yes, you can do problems like this, and that's nice, but there doesn't really seem to be another purpose besides that. But I assure you that with this last theorem that we are going to go over, it's going to be a much more general statement of Fermat's little theorem, and this will truly help us in solving problems. Now, that wasn't to downplay Fermat's little theorem. In fact, Fermat's little theorem was the first thing was found before this more general form, Euler's theorem. Of course, it was Euler. Who else would it be? And it was truly a big revelation in number theory. However, Euler, being Euler, cracked the code, and he stated that, well, if I have some positive number, a, right, a is some positive integer, not just a number, but a is some positive integer, and I also have some n, not just a prime number, that is also a positive integer. I should have included it in the same statement, but it doesn't matter. Then I have that a to the phi of n is congruent to 1 mod n. Okay, first of all, what is phi? Well, phi of n, oh boy, that's gonna, phi of n is, is defined as the number of number of integers that are relatively prime to n, not m, n, that are less than or equal to n. Okay, kind of a long statement, right? So phi of n is the number of positive integers that are relatively prime to n that are less than or equal to n. I just realized I forgot r. Okay, there we go. So this is a lot more helpful. Or I shouldn't say that because again, I'm not trying to downplay Fermat's little theorem, but of course, being the more general form, we get more uses out of it. So, well, you guys might be thinking, how do I calculate phi of n? I mean, I can't just count it every time, right? I mean, for 8, the integers before it are, 1, 2, 3, 4, 5, 6, 7, and 8, and if we count all the numbers that are relatively prime to it, we find that we cancel out all of the multiples of 2, and thus phi of 8 is 4. So how do we calculate phi of 8? Or how do we calculate phi of n for any n? Well, there are some properties that we should know about the Euler totient function. So first of all, the property of this is that it's multiplicative, meaning that phi of m times phi of n is equal to phi of m n if the greatest common divisor of m and n are relatively prime. Cool. So we basically, what this tells us is that it's we only need to know how to calculate phi of primes and powers of primes, and then we can pretty much find phi of anything. Well, how do we calculate phi of a power of a prime? So phi of p to the n, or maybe I should say p to the k since I've already used n. Phi of p to the k is going to be equal to p to the k minus p to the k minus 1. And the reason for this is just a simple counting problem, right? Say, first of all, there are p to the k different integers that are less than or equal to p to the k, different positive integers that are less than or equal to p to the k, right? And if we want to find all of the numbers that are relatively prime to p to the k, i.e. any multiple of p, then all we have to do is divide p to the k by p, which is p to the k minus 1. And we just have to subtract these multiples of p from this set of p to the k integers, and that is how we get this expression. So now that we know this, we can find phi of any number, of any positive integer that we want. So hopefully you guys have learned something. I know it was a bit of a rambly episode, kind of a lecture more so than like a problem-solving walkthrough, but I promise that next video we will be going over an AMC problem that employs all of these. So yeah, I hope you guys enjoyed, hope you guys learned something, and I'll see you next time.